Alright folks, hello and welcome to this video example. In this video we'll be looking at section 1.3, the distance formula. Please follow along on your note sheet and copy down the fill in the blanks as well as the examples so you have them for reference and for future study. So let's get right to it. The essential question for this lesson is, where does the formula come from? For many times in geometry we're going to be looking at various formulas. I want you to consider the fact, where did they come from? How did we get to them? And the important math word for that is how to derive them, or to show where they came from. These formulas didn't come from nowhere. They didn't drop out of the sky. I didn't find them on my desk, and you didn't find them under your shoe one day when you stepped in gum. They were found by mathematicians thinking carefully about problems and finding formulas that always work in every case. So let's get to it. We're going to look at the distance formula today. Recall, the Pythagorean theorem says that in a right triangle, a squared plus b squared equals c squared. This is an extremely important theorem that we'll look at later in the year. But right now, I want to show you how this theorem leads us to the distance formula. And we're going to do that through an example. First, let's look at example 1. Find the distance between point A, 2, 1, and point B, 5, 6. So I've zoomed in here so it'll be a little easier to plot the points. You can do approximately using the same scale, but 2, 1, that'll be point A right about there. And 5, 6 will go over 5 up 6, and that will be our point B. So the question is, what's the distance between those 2 points? And remember, that's defined by the length of this segment, the straight segment from A to B. If we can find that length, we know the distance. So, how does this relate to the Pythagorean theorem? Well, the next step is going to be to take your segment, whatever it is, and construct a right triangle using horizontal and vertical components. Here's what I mean. I'm going to go from point A over until I get to the x-coordinate of point B, and I'm going to go from point B down until I get to the y-coordinate of point A. These will meet at a right angle, forming a right triangle. And I just want you to notice that you can do this with any segment or any slanted segment. So for example, if I were to draw another slanted segment there, we would easily be able to construct a vertical component and a horizontal component to make a right triangle. So this method works for any slanted segment, and that's what we're going to use to find the distance right now. So according to the Pythagorean theorem, we know that a squared plus b squared equals c squared, and I just labeled the legs a, b, and c. And we're going to calculate their lengths and use the Pythagorean theorem. Remember, it doesn't matter A or B if you switch the legs. That's okay, but C has to be the hypotenuse, which is across from the right angle. So, what is the length of A? I can count 1, 2, 3, 4, 5 units. So A equals 5. And what is the length of B? It's 1, 2, 3 units. B equals 3. And now I can plug into our formula to get the distance. Let's do that. Please follow these steps and write them down. A squared would be 5 squared. B squared would be 3 squared equals c squared. Then we have to do a little bit of algebra. This is 25 plus 9 equals c squared, which is 34 equals c squared. And then if you remember from Algebra 1, to solve a square root equation, you want to take the square root of both sides. And normally when you do that, you would have two answers, a positive and a negative. But in this case, we're concerned about lengths, so we're only concerned with the positive root. So taking the square root of 34 and the square root of c squared, I get c equals approximately, and you can plug this into your calculator, 5.8 units. And we have just found the distance using the Pythagorean theorem. Next up is example 2. And this is a practice or an exercise in generalizing or generalization. We're going to generalize, or in other words, show that our previous procedure or method works for any numbers at all. So instead of taking points 2, 1 and 5, 6, we're going to use variables, x1, y1, x2, and y2. Now notice those little numbers are not exponents. They're technically called subscripts, and they just denote that x1 can be any random x, and x2 could be any random different x. Or they could be the same. but they're just variables that we use, and to show that they're both x-coordinates, we use the letter x, but to distinguish them and show that they could be different, we use those subscripts. So they have nothing to do with exponents. So notice this coordinate plane is not labeled with any scale, and that's because I don't want it to be. I want it to be completely arbitrary. Any points we pick, let's just say I pick a point here. I don't know what the values are, but x1, comma, y1, we'll plot it, and some point over here, x2, comma, y2. And again, I want you to notice that the distance formula or the procedure we're using is going to involve slanted lines. If you have a horizontal or vertical line, you don't need any special formula because you can just count. Boom, boom, boom. It's 3 units. Boom, boom, boom. 3 units. However many left or right or up or down, you simply count it. But when it is a slanted line, you're going to need a different procedure, and that's why we use the distance formula. So again, let's follow the procedure with the Pythagorean theorem. I'm going to draw the vertical and horizontal components of our right triangle, and we want to know the lengths of those. How much is this length, which we can call A, this length, which we can call B, and then we can square them and add them up to find C squared. So this is a little bit trickier because we don't have numbers, but I want you to refer back to the previous example to see how we can solve it. So there's our previous example. I just copy and pasted it in there. And I want you to see, I just counted the units to get the lengths of A and B. So for example, for this length here, this vertical length, I simply counted how many units up and down. But I want you to notice another way we could have done it. And that's by doing subtraction. And we could have done 5, 6, remember this is 2, 1. To get the vertical component, which is 5 units, we could have subtracted the y coordinates and done 6 minus 1. Taking both y coordinates and subtracting them, we get our distance there of 5 units, or length of 5. Same thing with the x's. If you wanted to, you could have done the 5 minus the 2. To get this length, 5 minus 2 will give us a length of 3. Now that's relevant because we're going to use that subtraction procedure in our generalization. So going back to this picture, we have lengths A, B, and C, and using the idea of subtraction, we can know that B is going to be equal to the larger x-coordinate minus the smaller x-coordinate. In this case, we'll take x2 minus x1 because x2 is further to the right, and that's the length of B. Take the larger minus the smaller, as we did in our number example. The length of A will be the larger y-coordinate minus the smaller y-coordinate. Or in this case, that will be our y1 minus our y2. So A will equal y1 minus y2. That's a vertical equal sign, which sometimes mathematicians will use in diagrams. And so we can set up our formula. It's a little bit more messy, but it's still the Pythagorean theorem, using a squared plus b squared equals c squared. We can now replace a and b with what we've got. So a squared is equal to y1 minus y2 squared. Actually, I'm going to write it down at the bottom so I have a little bit more room, plus our b squared, which is, again, remember this part, x2 minus x1 squared equals our c squared. Okay, and then if you were to solve this equation for c, it's going to get a little messy, but we could do it. How would you do that? I'm just going to zoom out so we have more room. You would take the square roots of both sides. Again, take square roots. And if you take the square root of this side and the square root of this side, you get this whole big concoction. C equals the square root of y1 minus y2 squared plus x2 minus x1 squared. And this is an example of the distance formula. It's going to be a messy expression, something like this. There will be a few minor changes to it that I'm going to show you on the next slide, but that's how you get it, and that is the derivation, or where it comes from. It comes from the Pythagorean theorem, as we've just shown. So on this final slide, I'd like to write out the distance formula as it's formally and commonly given, and that states the distance between any 2 points is given by the formula d equals, d standing for distance, the square root of, parentheses, x2 minus x1 squared plus y2 minus y1 squared. And substituting values for x and y will allow you to find the distance between any 2 points. You'll notice that the 2 and the 1 may have switched order on this slide compared to the first, but technically that's not going to matter because that's only going to change the sign of the number, and because it's squared, the result of squaring something is always positive. Think about -2. When you do -2 times itself, it becomes +4. And if you have +2 times itself, it's also +4. So it actually doesn't matter which order you're going to put these in because they're going to be squared, and that's going to give you the correct result. What does matter is that you're subtracting x coordinates and subtracting y coordinates, because if you don't pick the right coordinates, then the distance formula will not work. It does have to have the x's subtracted and the y's subtracted in order for it to work. For now, you can round your answers by taking the square root in the calculator, but we'll talk about how to find exact answers next class. So let's finish up these notes. In summary, you don't need to write this down, but just pay close attention. We did 4 things. 1, we used the Pythagorean theorem to find the distance. Next up, we derived the formula. We showed where it came from using the Pythagorean theorem. And that's a highly sophisticated mathematical task, something expected in geometry, and we will do more of. Next, we stated the formula. On the previous slide, in formal terms, we said this is how you can calculate any distance. And finally, I'd just like to round this off by saying we now have 2 very important formulas that will be used throughout the course. We know how to find the midpoint between any 2 points. That's on your notes. And we know how to find the distance between any 2 points. That's on your notes. So save that 2-sided note sheet and replay any parts of this video you didn't understand so that you can come in on Tuesday with any questions on the lesson. Thanks so much for watching this video lesson.